All right, let's go. Okay, so today we are now starting the chapter called Number Theory. Number theory, theory of numbers. We'll be doing a lot of basic arithmetic type stuff in this class, or in this chapter. We'll be doing a lot with arithmetic, plusing, adding, multiplying, dividing, doing that on certain sets of numbers, limited subsets of the integers. Talk about prime numbers a bit in this section, and how to divide integers. Well, I don't really know how to give you good intuition for number theory. Those of you who are already doing some computer science courses will see some familiar stuff, and this section will be easier for you, so you'll see some where it's relevant. But maybe we'll just jump into it rather than me trying to give you a high-level view of the things you cover in number theory. So, just looking at the integers as they are, we already know how to do some basic things on them. We know how to add integers, we know how to subtract integers, we know how to multiply integers. Those are all pretty straightforward. But if you remember clear back to when you were second or third graders, whatever it is, and you learned division, you came across a problem. So if I asked you what was 9 divided by 3, what's the answer? 3. But if you go ask some little kid what's 10 divided by 3, what are they going to say? It doesn't work. It's broken. And then you learned a little bit later that it's 3 with a remainder of 1. Perfect. So that idea right there, 3 with a remainder of 1, is exactly what we're going to be talking about for this whole lecture. Yep, sounds really simple, and it's going to come back to kick your butt. So you better pay attention.
Okay.
Same way that counting sounds simple, right?
Yeah.
Well, division seems simple. Let's see how simple it is. Now notice that when I said, we'll look at 12 divided by 3. What's 12 divided by 3?
4.
Oh, this one's 4, oops. But when I did 13 divided by 3, what is it? 4 with the remainder of 1, right? Now notice I said 4 with the remainder of 1. Why didn't I say 3 with a remainder of 5? You remove as many 3's as you possibly can without making your remainder negative, right?
Yeah.
And we also didn't say it's 5 with a remainder of negative 2. We said it's 4 with a remainder of 1. So notice when I say 13 divided by 3, there are only 2 possible numbers that you can put here and here that make this true. I could have only used 4, remainder 1. That is the one and only answer to the question I asked you. 4 with a remainder of 1. Right? Not 5 with a remainder of negative 2. Even though if you did the math, you'd still get 13 and 3. Right? 13 is 5 times 3 when you add a negative 2. Notice that when you say 13 divided by 3 is 4 with a remainder of 1, you're saying 4 times 3 plus 1 gets you back to 13.
Yeah.
Right? So, similarly, I could have said 5 with a remainder of negative 2. Notice 3 times 5 is 15 minus 2 is 13. But we're saying, no, we're always talking about this. We're never talking about things like this. So there's one and only one set of numbers that we're talking about when we're talking about this division with a remainder. You with me? Mm-hmm. Okay. So, let's get our big theorem of number theory. Warning, this theorem doesn't go away. This is a theorem you use over and over again all throughout this chapter. You use this for number theory like you use sample spaces for probability and statistics. It's everywhere. It's not going away. You need to understand this. So pay close attention. And I think if you get this theorem, the rest of number theory becomes pretty easy after that. At least what we cover in this class. Okay. So let a and b be integers with b greater than 0. So we're going to talk about always dividing by a positive number. We're not going to talk about dividing by a negative number. A is going to be our numerator. We don't care what that is. But b is going to be our denominator. We're always going to divide by a positive number. So let a and b be integers where b is greater than 0. Then there exist unique numbers, q and r. There exist unique integers, q and r, such that a is equal to qb plus r. R is a remainder. Q is this number. We call it the quotient. Quotient remainder. Quotient remainder. There exist unique q's and r's, namely 4 and 1, such that 13 is equal to 4 times 3 plus 1. You with me on that?
Yeah.
Now this and how it's capturing that idea? That is not the whole thing. I can't believe I missed this. Where, sorry, let me write it up here and then we'll just plug it in back down there. Because we limited the remainder. Where our remainder is always greater than or equal to 0 and less than the thing we're dividing by. So that goes here. Sorry. So there exist unique integers, q and r, such that a is equal to qb plus r, where r is a positive number less than b. Right? We can't have our remainder bigger than the number we're dividing by, otherwise we want to take away another b and make r smaller than the number we're dividing by. But it's perfect we find if r is 0, right? Remainder 0, those are the ones we like the most. Everyone understand what this proof is saying and how it's just exactly what you did way, way back in 3rd grade or whatever when you were doing division and you had a remainder. Q's, what you said the division was, r's, what you said the remainder was. Quotient, remainder. Good? Wonderful. Now we're going to prove this here. And we're going to do this theorem in 2 steps. First I'm going to prove, so for any 2 integers you give me a and b, where I know b is positive, I'm going to show that there exists integers q and r, such that a is equal to qb plus r, where r satisfies this inequality. And then once I show that there are integers that satisfy it, then I'm going to show that they're unique. So we're going to kind of break this into 2 proofs. You follow that?
Okay.
So first I'm just going to prove that there are integers, q and r, such that this is true and this is true. You with me? We're going to do this with proof by smallest counter example. Okay?
Okay.
So first I'm going to find, so maybe we'll just start. So let a and b be any integers where b is greater than 0. Right? And now I'm going to let capital A equal the set of all these differences for any integer you pick. Notice that if I take this equation right here and I solve for r, I get r is equal to a minus qb. Why am I putting that set? R is equal to a minus qb. This is the set of all the integers that we get when we decrement a by b's. Decrement. Remove a b from it. I'm going to remove it so plug in 0 for k. This is like all the possibilities for r. R is going to be a particular one of these numbers. So a is a set of all the things of this form. The right-hand side of this equation. A is a set of all the things of this form. And r is going to be a particular one of those. So let me write out a, we'll write it over here, for particular numbers. Give me a little a, 19. Give me a little b, 3. So a equals 19, b equals 3. If we were talking about that case, we're talking about 19 divided by 3. What is the big A equal to in this case? It's equal to everything you get when you plug in just an integer for k. Plug in 0 for k, plug in 1 for k, plug in 2 for k, plug in 3 for k, plug in 4 for k, etc. So there's infinite things. When we plug in 1 for k, what do we get? So when I do 19 minus 1 times 3, what do I get? 16. When I plug in 2 for k, what do I get? Maybe I'll start with 19 here. So this would have been counting down. Maybe we'll start with 21. Or 22. Plug in negative 1 for k, what do I get? 22. You follow me there? 19 minus negative 1 threes is 22. Okay, now 19 minus 0 threes, 19. 19 minus 1 3, 19 minus 2 threes, and we keep going. We're eventually going to get 1, then we're going to get negative 2, negative 5, negative 8, and it's going to keep going forever. right? This is what the A looks like. All these differences you can get for every possible integer k. What we're going to say is that the smallest positive integer you get out of here is our remainder.
Okay.
So in this special case, our remainder is going to be 1. Okay?
Okay, yeah.
That's where we're ultimately going. But, so notice it's going to be the smallest element in A when I get rid of the negative numbers. So I'm going to get rid of the negative numbers, prove that A is not empty, and then take its least element, which will be 1. You with me? Okay. So first thing I do, okay, so here's A. It's a set like that. Now I let B be A intersects with the natural numbers. So B is the same exact set, but now we got rid of all our negatives. And that ends. Right? B is just A intersects with the natural numbers. So now I know B is a subset of the natural numbers. By the way, ordering principle, I now know B has a least element. If it's non-empty. So I need to show it's non-empty. If it's not empty, it has a least element, and I'm going to call its least element R. Okay? So here to here is going to seem like we're doing a bunch of weird stuff, but remember, all we're trying to show is that B is not empty. We're not proving stuff that we're using later, we're just trying to show that B is not empty, so don't get lost in the details. You with me?
Yep.
Okay, so trying to show B is not empty, we handle two cases. The number that we're dividing is greater than or equal to 0 or it's less than 0. Notice if the number is greater than or equal to 0, it's always going to be in there. Right?
Yeah.
It's going to be, when you subtract 0 B's, is the number that's going to be in here. So if A is greater than or equal to 0, it's always going to be in your set. Let me draw another case where we have negative numbers, so this helps you think. So let's do A equal to negative 13, B equal to 4. What would the set look like in this case? So let's do negative 13. When we plug in 0 for k, we'll just do, that would be minus 13, right? Plug in 0 for k, we get minus 13. Plug in negative 1 for k, what do we get? Negative 9. Plug in negative 2 for k, what do we get?
Negative 5.
Negative 5. And then we get negative 1. And then we get 3. And then we get 7, etc., right? Counting up by 4. So notice that A, whatever A is always in. Down here in this case, this would be A. And then B would be starting at 3, 7, 11, etc. So two different examples of this exact proof. Don't get confused by the fact that we have two examples. So in one example, here's what A and B are. If little a is this and little b is that, here's what A and B look like.
Okay, but
If little a is this and b is that, here's what A and B look like.
the lowest one in B is not the remainder.
It is a remainder. And we'll come back to that, but it's wonderful that you're noticing this. You're saying, when you do negative 13 divided by 4, what is it?
Negative 3 remainder 1.
You're saying negative 3 remainder what?
1.
Not remainder 1, remainder negative 1, right?
Okay.
That's what you're trying to say. But our remainder always has to be positive. So, negative 13, we'll write up here, negative 13 is equal to negative 4 times B plus, in our case, 3. So the remainder is 3, not negative 1.
What the heck?
Now, when you get the negatives, it's real easy to figure out what the remainder should be. So you got a remainder negative 1, just add one more b to it, and that will get it back positive. Because you're just adding and subtracting b's to the number that you start with.
Then what is B?
You start with a and you start subtracting b's, or you start with a if it's negative and you start adding b's, as many as you can, until you have the smallest positive number as your remainder. How many times did you do it until you got your smallest positive number as your remainder? That's your quotient.
Wait, no, you did that wrong because negative 4 times B is...
What's negative 4 times 4?
Negative 6.
plus 3.
Oh.
We'll do more practice with
Wait.
those to help you see it.
Wait, where did we get the negative 4?
That's the quotient.
What was it? No, 4 is.
Negative 13 divided by 3 is negative 4 with a remainder of 3. Because negative 4, we have negative 4 b's
Aren't we down
with a
here?
remainder of 3.
Aren't we down here? Why are you using that 3 instead of that 4?
This, I just need space to write. That's these numbers up here.
Okay, where did you get the negative 4?
That's my quotient. I'm finding the numbers. So I know it looks like this. I know I need some number of b's plus my remainder to get negative 13. The same way that when you did 13 by 4. Let's draw these hand in hand. When you did 13 is equal to, I don't know why I'm putting a b there instead of a 4. We know b is 4.
Mm-hmm.
So I'm doing 13 divided by 4 and negative 13 divided by 4, right?
Yes.
You know, when it's 13 divided by 4, how many 4's can I take away to get my smallest positive number as a remainder?
3.
I take away 1, 2, 3, and that gets me down to 1 as a remainder, right?
Yes.
So this is equal to 3 4's plus 1.
Okay.
Okay, what about this one? How many 4's do I need to add to that to get my smallest positive remainder? Negative 4 with a remainder of positive 3.
But how do you know that?
How did you know it here?
You just do cuz.
You just do cuz, exactly. You just do cuz here. Here's how it's going to work with the negative. So the positive one's very intuitive to you.
Yes.
Here's how the negative one's going to work. The negative here is going to be 1 bigger than what you're used to. And the remainder here is going to be adding this one more time. Right?
Yes.
So you want the answer to be, you wanted the answer here to be negative 3 times 4 minus 1. But we can't have a minus 1, so I need to add one more 4.
Okay.
And if I add a 4, I need to subtract a 4. So subtract and add a 4. Subtract a 4 from this, add a 4 to this. So if we subtract another 4 from here, now we're subtracting 4 of them. Add a 4 to this gives me plus 3. So that's always going to, you're going to need to take one more away from that and add one more to that. And you'll get where you want to be. That make sense?
Yes.
Once you work with them enough and do a bunch of examples, you'll start to see connections in your head and it'll start to feel natural to you. The same way that this just feels natural to you. And when you ask someone why, they say, well, just cuz. Just think. It just is. Right? Okay, anyway, so we're doing our proof over there. And we say two cases. Either A is greater than or equal to 0, or A is less than 0. These are the two cases that we're breaking it up into. B always has to be greater than 0, that's given to us. So A is the only cases that we care about. If A is greater than or equal to 0, then A, which is always in big A, is also going to be in B. But if A was less than 0, then when we got B, when we intersected with the positive numbers, notice that we got rid of our A. You with me?
Okay.
Yeah.
Remember, all we're trying to show is that B is not empty. So in this case, we know B is not empty because at least A is in there. Here, we need to show B is not empty, and we can't say that A is in there. So this one's the only one that's a little bit tricky. So let's go back to the proof. If A is greater than or equal to 0, then A is the same thing as A minus 0 times B, and therefore it's in B. Right? B is a set of all things that look like this that come out positive. If you can write it like this, as A minus some number of B's, and it's a positive number, then it's in this B. You with me? So A can be written that way, and A is greater than or equal to 0, therefore A is in B. That's the simple case. Now we got to handle the case where A is less than 0.
Is 0 in the natural numbers?
Yes, in this class it is. In this class, 0 is a natural number, so yeah, when we intersect with the natural numbers, we still have our zeros. Which we want, because a remainder of 0 is very common.
Yeah.
Yeah. Anyways, so now let's look at the bottom case over there. When A is less than 0. So if A is less than 0, then there is still some integer, I may call it k prime, such that k prime is less than A. No matter how small of a negative number you pick, like negative 10,000, I can always find a smaller negative number, negative 10,001. Right? It could be A minus 1. That's what this could be. You follow me so far?
Mm-hmm.
So k prime is just some number more negative than a. If a is negative 13, k prime could be negative 5,476. Just some negative number smaller than a, less than a, to the left of a on the number line. That's what I mean by smaller. You with me so far?
Yeah.
Okay. So, notice that b is a number greater than or equal to 1, right?
It's greater than 0.
So,
Is
b is some positive integer. That's what we know about b. b is an integer greater than 0. So I know that there's some integer k prime that makes this true, which means when I multiply both sides by b, it's still true. Since b is positive, we don't have to flip the inequality. You with me? And notice that since a is negative, then a times some number that might be bigger than 1 is less than or equal to a times 1. Right? Negative 19 or negative 13 times an integer greater than or equal to 1 is always less than or equal to negative 13. Because the bigger the integer we multiply by, the smaller we make the number.
Mm-hmm.
So, hopefully this inequality, and this inequality all make sense to you. You good with this whole thing?
So wait, you're saying if you multiply a negative number by a positive number, it makes it larger than...
It makes it more negative. It makes it less than.
Okay, but that's...
So
isn't
if
that
I
saying
know
that
that
you're making
negative
it
19
greater?
is less than negative 5, then I know that 100 times negative 19 is less than negative 5 times a number smaller than that, 1. So the b that I multiply by, I know is an integer greater than or equal to 1. So b is greater than or equal to 1, and 1's 1. So when we multiply by b, we could have only made the whole thing smaller.
I thought you were saying the other side would be greater. I was getting
No. So this inequality is just, we know this is true. If you have an inequality, multiply both sides by a positive number, the inequality is still true. Right?
Yeah.
And then more of a negative number is less than or equal to 1 of a negative number, if that more is greater than or equal to 1.
Yeah.
So b is greater than or equal to 1, so this part's true. You with me? So all we were trying to establish is there is some negative integer k prime, such that k prime times b is less than a. That's all we were trying to get to so far. So if we're good with this, how we got there, you kind of don't need to keep track of it anymore. I just don't want you to get confused in the details. Well, if a number is less than a number, what does that mean? It means that, let me draw up here to keep it simpler. If negative 3 is less than 5, what does that mean? It means 5 minus negative 3 is a positive. A bigger minus a smaller is positive. A bigger minus a smaller is always positive. You with me?
Yeah.
A bigger minus a smaller is always positive. If I take Leah's height and I subtract Rhoda's height, I still have a positive number. Because Leah is taller than Rhoda.
Oh.
A bigger minus a smaller still leaves some positive value.
Okay.
If it left a negative value, then Leah would have actually been smaller than Rhoda, not greater than Rhoda. So, if this number is bigger than this number, then this number minus this number has to be positive. That's actually how we define greater than. It's one way to do it. It's the way we do it in calculus. We say that this is greater than this if their difference is a positive number. Anyways. So if a is greater than k prime times b, then a minus k prime times b is positive. You with me?
Yeah.
Which gives me that a minus k prime times b is in b. It's a number greater than 0 that can be written as a plus an integer times b.
A minus an integer.
Plus, we could have written this as plus negative k prime times b. Same thing. Subtraction is addition, right?
Yeah.
So this is a plus an integer times b. You follow me on that? Anything weird? Okay. So it can be written as a plus an integer times b, and it's greater than 0. Therefore, it's in this set b. What was that set b? That set b it was A, all the numbers that can be written this way, that are greater than or equal to 0. Greater than or equal to 0. We know it's greater than 0, but that also means greater than or equal to 0. So remember, all we were doing here is showing that B is not empty. That's it. It's easy to get lost in the details, but keep track of what we were doing. All we were saying is B is not empty.
Right.
So you good with B is not empty?
Yes.
Okay. So if B is not empty, then what do we know? By the well-ordering principle, it has a least element. And we're going to call its least element R. It's going to turn out that R is the remainder. The remainder, the smallest element in B over here was 3, is going to be the remainder. The smallest element in B over here was 1, is going to be the remainder. So that's where we're headed with this, but keep track of what we're saying. So, by the well-ordering principle, there exists a least element in B such that R is the least element of B. Okay, so we've got that. Then, if R is in this set, what does that mean? That means R is equal to A minus some integer times B. Oh, it's minus some integer. I was saying plus down here. Sorry, it was minus. Is that what you were pointing out?
Yeah.
Sorry. Yeah, minus. So we don't need to think about this as plus. We could have thought about it minus. Anyways, so since R is in A, well, R is in B. If R is in B, R is in A. Because B is a subset, right? So if R is in A, what does that mean? That means that there is some integer that you can plug in for K, such that R is equal to A minus that integer times B. Right?
Mm-hmm.
So over here, the magic integer was what?
Wasn't it like...
What number do I have? How many 3's do I have to subtract from 19 to get 1? 6. So there was some integer that I plugged in for K that gave me the R. Right? There had to have been. In that case, it was 6. So over here, since R is in this set, then there has to be some integer I can plug in for K so that R is equal to this thing when I plug in that integer. Over there, it was 6. We're going to call that integer Q. So since R is in this set, then there must exist some integer Q such that R is equal to A minus Q times B. Right?
Mm-hmm.
Yeah.
You follow that? Didn't know division was so hard, did you? Alright. So R is equal to A minus Q times B. And notice also that we know that R is greater than or equal to 0. How do I know that R is greater than or equal to 0?
Because of what you just proved.
It's in B. B is intersected with the naturals. So it has to be a natural number. So we know that R is greater than or equal to 0. And we know that there's some integer Q such that R is equal to A minus Q times B. The last thing we need is that R is less than B. Once we show that R is less than B, we're done with showing this proof, except for the uniqueness. So here's what I've shown. I've shown that for any two integers A and B you pick, I can find an R and a Q such that this equation is true. Notice that this equation and this equation are the same thing.
Mm-hmm.
Just shifting the symbols around a little. So I've shown that for any A, B you choose, I can find a Q and R that make this equation true, where R is greater than or equal to 0. Now I need to show that R is less than B, and then we've shown that we can find integers that do it. And then I need to show uniqueness, and then we're done. You with me?
Mm-hmm.
Alright. So we need to show that R is less than B. Okay. Assume by way of contradiction that R is greater than B. And let R prime, we're just going to call A minus Q plus 1B. It's going to be what you get when you subtract one more B from R. I'm going to show that R prime is also in B, and that R prime is less than R. Contradiction. R is the least element of big B. I'm going to let R prime equal this thing. I'm going to show that R prime is also in big B, and that R prime is less than R. Contradiction. R is the smallest thing in big B. Make sense?
Yeah.
Mm-hmm.
Alright, that's what we're going to do. So let R prime equal this thing, then R prime is equal to A minus QB. Just distribute the B across those.
Mm-hmm.
So R prime is equal to, notice that's R minus B. R minus B. Here's R, in case you lost track.
Oh, yeah.
So when you plug that in, for that, that's just R. You follow that so far? So it's equal to R minus B. So R prime is equal to R minus B. But since R is greater than B, then R minus B is greater than 0. A bigger subtract a smaller is positive. A bigger subtract a smaller is positive. You with me?
Yep.
So the point is, R prime is equal, so look here, we said R prime is equal to A minus some integer times B, and R prime is greater than 0. Therefore, R prime is in B.
Yeah.
So then R prime is less than R, and R prime is in B. Contradiction.
Wait, how is R prime less than R?
Yeah.
It's R minus a positive number. R prime is equal to R minus B.
Okay.
So, yeah, from this line we see that R prime is R minus a positive number.
So it has to be less than R.
So R prime is definitely less than R, and is greater than 0. And R prime is in B. So R prime is in B, and R prime is less than R.
That's not possible because R is the smallest element in B.
Perfect. By definition, R is the smallest thing in B. We can't find something smaller that's also in B. That's a contradiction. There's our contradiction. Okay, so R couldn't be greater than B, so R had to be less than B. There we go. That's the hard part of the proof. The hardest part of the whole section is getting up to there. We just barely showed that for any two integers A and B you choose, I can find Q and R such that this equation is true, where R is between 0 and B.
Okay, wait,
Including
what
zero.
about if it's equal to it?
What about if what's equal to what?
So you proved that R can't be greater than B, but you didn't prove it's equal to B.
R is the least element in big B. You're saying,
I'm saying, how does proving that R is greater than B proves that R is less? And that if you get a contradiction when R is greater than B, then how does it prove that R is less than B? Can't R be equal to B?
oh, you're saying we overlooked the case where R is equal to B. That is a good point. Let's think for a second why R, by way of contradiction, assume that R is greater than or equal to B. Then R minus B is greater than or equal to 0. Which we're still finding out. That's a good point. Because R prime is still a natural, which is what we want. And it's still greater than R, because it's still equal to R minus a positive number. Good catch. So yeah, there's nothing wrong with turning those into greater than or equals, and we should be good. Okay. So now we proved existence, we just haven't proved uniqueness. All we need to prove now is uniqueness. So I proved that you pick A and B, I can always find a Q and R, such that this equation is true, where my R is in between 0 and B. It remains for me to show now that there's only one set of numbers Q and R that make this true. We know that there is some set of numbers that make it true. Now we're going to prove that there's only one set of numbers that make it true. So that's the next part of the proof. It remains to show that R, Q are unique. Okay, assume by way of contradiction that there exists R prime and Q prime. This is no reference to R primes and Q primes that we've used before in the proof. It's kind of like a new proof now. Assume by way of contradiction that there are two other numbers, R prime and Q prime, such that A is equal to Q prime times B plus R prime, where R prime is between 0 and B. And our R prime and Q prime are not the same numbers as R and Q. And we're going to prove that they are the same numbers, which is going to be our contradiction. So, since A is equal to Q prime B plus R prime, and A is equal to Q B plus R, then these two are equal to each other. They're both equal to A. You follow that? This was equal to A, this was equal to A, therefore they're equal to each other.
Yeah.
Good? A little bit of algebra. Put my R's over here and my QB's over there, and factor out the B from the Q's. Anything weird there? You see the algebra? Okay. what does this mean? R minus R prime is equal to B times an integer, or in other words, B divides R prime minus R, right?
What? Where
Yeah,
did
what?
Q's go?
Q minus Q prime is just an integer, right?
Yeah.
So R prime minus R is equal to B times an integer.
Yeah.
So by definition, B divides R prime minus R.
Oh.
Okay.
Not this division. Divides way, way back, as in
Yeah.
an even number is a number that's divisible by 2. R prime minus R is divisible by B,
Yeah.
right? Which means that there exists some integer k. That's kind of weird that I went to k instead of just using q minus q prime. Might have done some redundant step here. Doesn't matter. There exists some integer k such that b times k is equal to r prime minus r.
Yes.
Right? We already know what that k is. It's q minus q prime. I don't know why I went through all this work instead of just using q minus q prime. Should have just used it. Okay. Also observe that 0 is less than or equal to r is less than r prime is less than b. It's important that you wrap your head around this part because it's all
R
going
is
to come
less
together.
than R prime.
Yeah, r is the least element that makes the statement true. R prime is some other element that happens to make the statement true.
Okay.
But it doesn't really matter the order of these two. I could have just as easily done a comma here, and it still would work.
Okay.
So we know that both r and r prime are numbers between 0 and b, not including b, right? And up here we're saying their difference is a multiple of b.
That means it had to be greater than B.
It just has to be a multiple of b. What's the smallest multiple of b?
B
B.
itself.
0. Right? You've got the right idea. Look, r and r prime are between 0 and b. What's the most distance that can be between these two numbers?
Nothing.
B minus 1. Look, if b were 10, then the biggest difference between these two numbers could be 9. You can make this one 9 and this one 0, and then their difference is 9. I can't make their difference more than 10 though, right? I can't make it more than whatever b is.
Yeah.
Does that make sense what I'm saying?
Yeah.
Okay. I know that their difference is a multiple of b, and I know that their difference can't even be 1b.
Yeah.
So what multiple of b is their difference?
0.
0. That's the only one it can be. It can't be 1. Oh, we're too big. Their distance isn't that big. It has to be a multiple of b less than 1. It has to be an integer multiple of b less than 1. That only leaves 0. Make sense? So the distance between these two things has to be 0. So k is equal to 0. Where k is this. You see that?
Yeah.
Since k is 0, that means q minus q prime is 0, so q is equal to q prime. Furthermore, since k is 0, r prime minus r is equal to 0, which means r is equal to r prime. So they're the same numbers. You see that? Proof by contradiction, therefore they're the same, and we're done. Uniqueness. Now I know this proof is a pain, and there's a lot going on for like side elements, like showing b is not empty. But if you can, and the whole proof's in your book, if you go through, reread this proof, make it make sense to you line by line, and you can just wrap your head around this thing, I think you will be fine for the rest of the chapter. Make sense? Okay. From here on out, the class just gets easy. So now we're going back to what we were doing at the beginning. Okay, so we did this proof, now we're going to use this proof over and over again. What does this proof basically say? It says we can do what we did right at the beginning. Well, I want to do 13 divided by 3. What is it? It's 4 with a remainder of 1. That's what it is.
Yeah.
Yeah? Yeah, we just barely proved that now. That you can do that. You can find two numbers that make it true, and those numbers are going to be unique. Those are the two unique numbers you can plug in. The quotient and the remainder. So let's do it. So 19 and 6. What's my quotient?
3.
3. What's my remainder?
1.
1. 3 and 1. Those are the two unique numbers that I can find where one has to be between 0 and 6, such that 19 is equal to QB plus R.
Yeah.
All right, let's do it for the next one. A is 37, B is 5. What's the quotient?
7.
7. What's the remainder?
2.
Wonderful. Next, A is 11, B is 2. What's the quotient?
5.
5. What's the remainder?
1.
Wonderful. Next one. A is negative 45, B is 6.
8.
8
And
Negative 8 and 3.
and 3. Negative 8 and 3. Good catch. All right, that one might have been a little bit harder for some of you. So what's the number that you wanted to say? You wanted to say 7, right?
No, I understood it.
Oh, you did?
Yeah, because of that.
You got it right from the beginning?
You already told
Is
me.
anyone confused by the negative 8? That just, we're good. All right, wonderful. Okay, let's do the next one. What's the quotient?
Negative 3.
Negative 3. What's the remainder?
2.
2. All right. What's the quotient?
Negative
296.
Negative 296. Divided by 1 is easy. What's the remainder?
0.
0. Okay. Nothing tricky there? Let me write one more here. What if we do A is equal to 17 and B is equal to negative 3?
Wait a second.
Can't do that. Undefined. We haven't dealt with that case. B has to be a positive number.
Yeah.
Okay, so don't get sucked into that. Good job. Okay. Some simple proofs. Clean up the stuff that we just scribbled in here.
How do we already prove this?
No. And I know why you say that, because we proved one way, but we have to prove the other. So, really quick, every integer is even or odd, but not both. We proved the but not both.
No, didn't we prove that every integer is even or odd?
No.
Thought we did.
I feel like we've done this.
I feel
But
like
not
we did the
both. Are you
first part.
saying we proved
We've
that
proved that
it
it can't be both.
Okay.
Yes.
Okay.
So we've done one.
Right.
Assume by way of contradiction that some integer, which we call it x in z, is even and odd. Well, what does that give us?
Yeah.
That gives us x, it can be written as 2k, and x can be written as 2n plus 1. It can be written this way since it's even, this way since it's odd. What does that give me? Substituting in 2k for x here, we get 2k is equal to 2n plus 1. Or we get, move my n over here, and then divide both sides by 2. So we get k minus n is equal to 1/2. Contradiction. I can't subtract two integers and get a non-integer. You follow the algebra there?
Yeah.
That's one that we already did. So it can't be both. Now we need to prove every integer is either even or odd. So 2. Let x be some integer. Here's one that we're interested in. We need to prove it's even or odd. Okay? Then there exists unique QR such that x is equal to 2q plus r, where 0 less than or equal to r less than 2. In other words, whatever x is, we can divide it by 2. And we'll get a quotient and a remainder. Right? Now, notice what we know about the remainder. What do we know about the remainder?
It's either going to be 1
Or 0.
It's 0 or 1. It has to be an integer greater than or equal to 0 and less than 2. 4. Maybe say something like observe. Is that right? Or isn't that not weird? That's neat. Observe that r is equal to 0 or r is equal to 1. Maybe make it really explicit, although I think you would have gotten it either way. equals 1, comma, then x is equal to 2 cubed plus 1 is odd. 6, if r equals 0, comma, then x equal to 2 cubed plus 0 is even. In neither case, it was even or odd. Remember that. Pretty simple proof.
Yeah.
Follow that? Anything weird? Okay. Two integers are congruent mod 2 if and only if they have the same parity. Now let's go back to congruent mod 2 to make sure this makes sense. 1. We'll prove it this way first. Prove that if they're congruent mod 2, do you remember what the same parity means?
Yeah.
They're either both even or they're both odd. Okay, so 1. Let A be in Z such that A is congruent to B mod 2. Right?
Mm-hmm.
So this is congruent mod 2. And we're going to show that this implies that they're both even or they're both odd.
Yeah.
Okay. 2. Then A minus B is equal to K times 2. It means 2 divides A minus B. Maybe write it out exactly how you're used to seeing it, so, since it's been a little bit. This is the same thing as 2 divides A minus B, which is the same thing as there exists K in Z such that 2K is equal to A minus B. With me? Okay. Here's all the hard parts. Now we are just going to use exactly what we proved over here. We know that every integer is either even or odd, not both, right? So I'm going to handle if A is even, show B is even, and then if A is odd, B is odd. Therefore they have the same parity.
Okay.
Okay, so 3. If A is even, that gives us that 2k is equal to 2n minus b for some integer n, right? Just substituting in. Oh, A is even. Oh, I did substitute it for A.
Yeah.
You with me so far? I know A is even. If A is even, then A can be written as 2 times some integer.
Oh, okay.
Just substituting in for A. With me?
Mm-hmm.
Which then gives us, I'm just solving for B, so move B to this side and K to that side. So we get B is equal to 2 times n minus K when you do the algebra.
Yeah.
Which gives us B's even. Everyone see the algebra there?
Yeah.
Anything weird? We just add the B here and then subtract the K here, and then factor the 2 out of the K in the end. Good? Okay. So now let's handle the other case. What if A is odd? If A is odd, what does that give us? That gives us that 2K is equal to 2n plus 1 minus B, right?
Which is.
Yeah, it's the exact same thing. Move the B over here and the 2K over there, and I get B is equal to 2n minus K, factor the 2 out, plus 1, which is odd. Follow that?
Yeah.
Nothing weird with the algebra?
Mm-hmm.
Okay, now let's go the other way. Assume, or let A, we'll just let A and B. Let A be in Z such that they have same parity. How do I want to do this? Should I just break up into its cases? Seems like there's an easier way. we'll just break it up into these cases. And I'm sure that there's a clever way to think about it, but I don't want to waste time coming up with it. So we'll just handle the case where they're both even and then the case where they're both odd. That's all the cases. If A, B even, then we can write A is equal to 2K and B is equal to 2N, which gives us that A minus B is equal to 2K minus 2N is equal to 2 times K minus N, which gives us that 2 divides A minus B. I think it's pretty simple thinking there. Anything weird? How do I show that A is congruent to B mod 2? I show that 2 divides their difference. That's all I was trying to show. So take their difference and show that it's equal to 2 times an integer. Therefore, 2 divides it. Maybe put one more step, which gives me that A is congruent to B mod 2. Good? Okay. Now, if you do the odd case, it's going to be the same thing. And then we'll be done with this. If A be odd, then we can write A is equal to 2K plus 1, and B is equal to 2N plus 1, which gives us A minus B is equal to 2K plus 1 minus 2N minus 1, because you distribute the minus through all of B. The ones cancel out, so that's the same thing as 2 times K minus N, which gives us that. I think we can just go straight to it. A is going to be mod 2. I think you'll see it all. Anything that needs explanation there? Kind of going fast because I think it's pretty clear that it comes out the exact same way as the previous case, right?
Mm-hmm.
Okay. Alright, so that's that proof. Definitions now. Definitions, we've been talking this way the whole time. Now let's just make it explicit, exactly what we're talking about. So let A and B be integers with B greater than 0. Then by the theorem that we started with, there exist unique integers Q and R such that A is equal to QB plus R. We define operators div and mod by A div B is equal to Q and A mod B is equal to R. In other words, when I say A div B, I mean what's the quotient. When I say A mod B, I mean what's the remainder. This mod is the exact same thing in computer science that you've already been dealing with. Exactly how mod works there, that was saying what's the remainder. That's exactly what that's saying. You're used to seeing it as probably the percent symbol. Same thing. Make sense? So let's calculate some. What's 19 div 6?
3.
3. What's the quotient when you divide 19 by 6? 3. What's 19 mod 6?
1.
1. What's 37 div 5?
7.
7. And what's the mod?
2.
2.
5.
5.
1.
1. Anyone confused how people are getting these numbers? Does it feel magical in any way? Okay. Continuing.
8.
8.
Negative 8.
Negative 8.
Negative 8. Good catch. Negative 8.
3.
3. 3.
Negative 3.
Negative 3.
2.
2.
Wonderful. Exact same thing we did over here. Just rewrite now a different way. No difference. We're just naming those operators now. Good? Okay. This last one is a homework problem. I don't know that I want to record it. I just want to help you get started because it's kind of a tough one, but I don't want you to have it recorded, so you have to pay attention. So get started recording, that's all the new material, and then help you get started on this problem. Well, we'll just record it. Don't go back and rewatch this for your problem. In fact, if it gets you to rewatch the lecture, maybe it's worth it. Anyways, let me help you get started on this problem because these definitions are kind of weird to work with when you start. So when I have A is congruent to B mod n, maybe I won't do the whole thing, but try and just help you get started to the point where I think you can take it from there. So I'm trying to show that A congruent to B mod n is the same thing as A mod n equals B mod n. Now, you might not remember, but way back when we talked about this, I said one way to think about it is A is congruent to B mod n if they have the same remainder when you divide by n. That's one way that I told you that you could think about it. That's exactly what this is. The remainder of A when you divide by n, the remainder of B when you divide by n. So if the remainders are the same, then A is congruent to B mod n. That's what we're proving. So you understand what we're proving here?
I think so.
Yeah.
And keep track in your head that this notation and this notation are very different things, right?
Yeah.
Over here we're talking about an equivalence, over here we have an equal sign. Here we're saying they're the exact same number, here we're saying two numbers are somehow the same. 21 and 11 are somehow the same when you divide by 10, meaning the remainders are equal.
Yeah.
Okay, so let's prove it. Before we even start this, here's the piece that's really going to help you keep things straight in your head. Well, we can start with let A be and blah, 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 blah. You don't need to say all the lets. So, let A be integers such, we don't even do that until we go this way or that way. So, maybe do my lets here so that you can see what I'm saying. Let A be in Z and N in N. So let A and B be any integers you want and let N be a natural number. In fact, we're going to divide by N, and I think we have to require N greater than 0, don't we? So yeah, not just a natural number. So let A, B, and N all be integers where N is greater than 0, because we're going to divide by N. Okay. The second step before we start doing the left and the right is going to be to use that theorem ahead of time. So by 35.1, there exists Q, R, and Q prime, and R prime, unique ones, such that A is equal to Qn plus R, B is equal to Q prime. Why do I keep, oh geez. Q prime n plus R prime, whereas 0 is less than or equal to R is less than n. Whatever integers A and B are, we can divide them by n. And we'll get a quotient for each of them and a remainder for each of them. You with me?
Yeah.
Okay. That's going to be the part you get stuck on when starting to do these proofs, is to realize what exactly these definitions are. Now, what is A mod n? It is R. A mod n is R. B mod n is R prime. So, it is a perfectly valid substitution to go from A mod n to, this is the exact same thing as, now we have this defined as A minus Qn. A minus Qn and A mod n, same thing. They're both R. Those are going to be the weird substitutions for you. You already know how to substitute with this thing, right? A minus B divides 2, or A minus B is equal to some integer times n. It's substituting for these things that might be awkward for you. So that's how you're going to substitute. Make sense?
Okay.
Well, now we're ready to actually start the proof. This is just some setup that you're going to use in your proof. So 3, now we're going to prove, doesn't matter which way first, we prove this way. We say, assume A is congruent to B mod n, right? That's going to give us, ultimately, that A minus B is equal to K times n.
How'd you get that?
A minus B, n divides the difference.
Yeah.
N divides the difference.
Yeah.
n times an integer equals the difference.
Okay.
Same thing? Okay. So that gets you to here. Which is the same thing as plus b. Sorry, no. Now we need to write a this way. So a is equal to k times n plus b, but we also know what b is now. It's this thing. So a is equal to k times n plus q prime times n plus r prime. Right?
Mm-hmm.
Which is equal to, factor out the n, it's equal to n times some integer, n times some integer plus r prime. You with me? Sorry, should have specified exactly what we're trying to do. I'm going to use this information, I'm going to use these substitutions, and I'm going to prove that r is equal to r prime, or in other words, that r is equal to r prime. Sorry, I should have specified that in the beginning. I get thinking about it and forget to talk out loud. So you understand where we're trying to go.
Yeah.
So I got a, and I've got my r prime showing up. Now, I can also say, another way that I can write a is equal to what?
Q and
Let me write clear down here. We also know that a is equal to n times q. Why do I keep doing g's? N times q plus r, right?
Yeah.
Up here, I know r prime 0 less than or equal to r prime less than n, and I know r is 0 less than or equal to r less than n. And I know that q and r are the unique integers I can use to do this.
Yeah.
Here, I didn't. Q and R are the unique integers. Q and R are the unique integers I can use to write a equal to n times q plus r, where r satisfies this condition. I also did a is equal to these ones. What does that mean? That means that is q and that is r. Now, we don't care about the fact that that is q, but notice that that is true. And r prime are now the same.
Yeah.
I don't see that.
Q and R are the unique integers. They are the only two integers in all of existence, such that a is equal to n times q plus r, where r is between 0 and n.
Yeah.
Well, I also have a is equal to n times some integer plus some number that's between 0 and n. Q and R are the unique integers that I can use to do that. Here's two other integers that I use to do that. There aren't other integers you can use to do that. Therefore, they're the same integer.
Okay.
So that is that, and that is that. You with me?
I think so.
Okay. So now we showed that r prime and r are the same.
So how do you do it the other way then?
The other way, you're going to substitute in for those. So the other way, Peter's trying to trick me into doing the whole thing. So if we do it this way, we say, assume A mod n is equal to B mod n. Or in other words, that's identical with R is equal to R prime, right? So then, A minus B is equal to A, did we do the Q first? Yeah. A minus B. Why did I do an R prime there?
Because it's
R
the same.
prime is R. Notice R's go out. Which is equal to n times q minus q prime. So n divides a minus b. And we're done. you don't quite get it, that's awesome.
That's
I didn't want
awesome.
you to completely have this problem. Let's erase it now. Of course, you can just pause and look at what I had. I probably shouldn't have recorded it. Oh well, this one's done. Okay, so that's it for new material. Try to do that homework problem without looking at this. See if you can put